Okay, welcome back, everyone. And it's a pleasure to introduce James Mattingly. I was trying to remember if we first met in 1996 or 1998 at a PSA meeting. Anyway, it was a while ago.
Didn't we first meet at Notre Dame at the
maybe
HFGR?
That might be it, and that was in the 90s in any case. So it's great to welcome James back to Western. He's been to Western for conferences before as well. He did his PhD at Indiana in the HPS department there in 2002, and he's currently a professor at Georgetown. He's written a book a few years ago on information and experimental knowledge. And recently, I wanted to ask you about this, a recent book on machine agency with a co-author. And today he's going to talk to us about ideal empiricism. So please take it away, James.
Thanks, Chris. Thanks so much for your indulgence. I've been very happy over the last few weeks since receiving this invitation to have an opportunity to take a look back at philosophy of physics. I haven't really been doing too much of that in the last many years. And instead, what I've been doing a lot because of my teaching situation is reading a lot of Hume, and I get to teach that a fair bit. And so I'm very interested in Hume's particular take on idealism. And I'm also struck by the fact that at least, I don't know, until the turn of the 20th century, idealism wasn't such a horrifying view in the philosophy of science. It was almost respectable in certain quarters. And strangely enough, I mean, if you think Michael Friedman was respectable, in the space-time theory, idealism, at least of the critical sort, was perfectly acceptable in certain quarters. But for some reason, and I'm not enough of an historian, and maybe, and now I'm looking at you, Wayne, because Wayne knows everything. But I'm not enough of a historian to know why exactly things went south for idealism in the context of quantum theory. I mean, one can speculate very well, but I prefer an historian to tell me. And so that's another thing that struck me is why is that a problem? And why is it that so many people, and I'm thinking about, Čáslav Bruckner and folks of that sort, who confronted with the results of the violations of Bell's inequalities, have been so concerned to keep the locality features that they grew up loving, and give up whatever reality they have to. But the kind of reality that they're giving up is of a very strange sort. And when they do it, they say things like the world isn't real or something like that. And so that's associated with a certain kind of idealism. But I'm hoping to show that that's not, or at least to indicate that that's not really the kind of idealism that one should want, but it's also not the kind of idealism that one really needs to be happy with the quantum theory. And I'll just say one more thing by way of introduction. I've never really worked on quantum theory, so I'm really here hoping to get some feedback on some preliminary ideas about this and so forth. And I expect, given the crowd, that's definitely going to happen. Okay. So here's the outline. I'm going to try to sort my way through a kind of an argument. It's not entirely respectable as an argument, but it has a sort of a half of a flavor of that. I'm going to speak a little bit about the nature of scientific theories and why one would be interested. Mostly, I'm saying that to give, after that, Bill Demopoulos a chance to say something. And then I'm sad to say I'm going to have to demur a little bit from his view of things, but not very much. And then that'll take us through the setting up for idealism. I'm using him, it's a weird thing to do, but I'm using Bill as my setup for idealism. And then I'll try to say something about the kind of idealism that I have in mind and why one might be interested in that, and why you might think that idealism of this sort is on the other side of what you might call an idealism-realism divide, on the realism side of which is the realism-instrumentalism debate. And so that's the main background contention of the talk, that's where that distinction lives. And then I'll try to connect all that up with some skepticism and relativity. And then then it'll be on to quantum stuff. And the quantum stuff that I'm going to be talking about is this whole literature that's now growing up around various extended versions of Wigner's friend, and how that's used to undermine a number of various theses in what you might call the realism position. And I'll try to say some critical things about those. And then I'll propose a completely nonsensical solution to all of this, and then that'll be that. And then we can all go have a drink. So why would you want a theory of theories? Well, these are some of the main kind of options that you might consider. You want to explain the logic of theory change. That for me was always kind of a hobby horse. If you understand how theories are structured, then you can understand a little bit about how they slot into each other over time. And it should be one of the main features of a theory that they're useful for making new theories. And so that's one reason. But another thing is that you might use that as a diagnostic tool when you're looking at particular theories. And sometimes that's a use for the discussion of the theory of theories. And finally, you might use it to think about a particular theory and whether that's any good, and what kind of general considerations this theory prompts you to reconsider. And maybe when you reconsider those, that'll move you away from that theory into something a little more, palatable. And as I say, I'm thinking right now about the quantum theory. Okay, so I think definitely a result of the investigation of the theory of theories is the understanding that they should explain the phenomena. And I think I would get in trouble if George Smith were still here, because I always did think that was what one of the main points to the Principia was, that you wanted to explain not laws, because he didn't think of them as laws, but to explain the phenomena that were the results of Kepler's investigation. Notably, one of the very few places in the Principia where explain even appears, explicare, but also exposui, is here exactly in this point of the Principia when Newton is considering the phenomena, and who already told us what the earlier today we already heard what the phenomena are, and it's quite an interesting thing that the only time phenomena are talked about in the Principia are these things: the features of the orbits, the laws of orbital motion, and what Newton took himself to have done was explain those with the force of gravity, and at least historically, the best candidate for explanation is locally acting causes, and is insofar as you can get that, people seem to want that, and you only give that up in contexts where somehow the data or the phenomena themselves make that difficult and resist that kind of an explanation. So here's one take on what scientific theories are. One reason for this is very old work of mine, but it's just worthwhile to point out that not all theory structures are even of the right kind of candidate to be engaged in the instrumentalism versus realism kind of debates. And so I was thinking of theories as the sets of models, the mathematical structures and so forth, but together with particular ways of picking out those models, what you might call formulations of the theory. And those are interesting because sometimes if you choose a different formulation, you might get the same classes of models, essentially. I don't want Jim to get mad at me right now, but if you do the connections for general relativity, you get almost the same thing if you do metrics. And yet, if you then want to take this theory, general relativity, and move it forward to make a change to it, for example, to try to quantize it or whatnot, what happens if you try to quantize metric formulations of general relativity? You get garbage, basically. And if you quantize the affine formulations of it, you don't get garbage. You don't get quantum gravity, but you don't get garbage. So there clearly different things come out if you try to modify a theory in one way of formulating it versus another way of formulating it. And that's all really this that slide is supposed to be saying. Okay, but it doesn't really matter for my purposes what your view is of the ontology of theories, because if you think of this as a kind of way a theory is used, it's going to be in a certain sense independent of your ontology of theories. It won't really matter whether you want to be a semantic theorist or inaptly named syntactic theorist or anything like that. Instead, you can still think of the way the theories function, the kind of role that they play in structuring our understanding of the world and so forth, is in this kind of tiered structure. You don't have to think of it this way, but it's available to you. And it connects up nicely with the way Carnap was originally thinking about things in his dissertation. You have this various layered account of what's going on in geometry. Geometry has its formal features, and your intuitive, way of understanding the thing. And then there's the actual physical geometry, coordinating various elements of the geometry with things in the world. That's not the exact same thing that's going on here in Michael's dynamics of reason, but they're not a million miles away. And this particular way of thinking about the role of theories was developed against a background of what he saw as an urgent kind of need to respond to Quinean skepticism about various kinds of analytic and synthetic distinctions in theories in general. And he didn't really take that head on, but instead developed a way of showing, at least in the way we apply the theories to the phenomena, that they do have a kind of distinct feature at various stages. You have to build a mathematics, and he's thinking principally about general relativity here, but you have to build a mathematics that's just kind of the venue in which you're going to do your science. And then the mechanical bits, for him in general relativity, this is the distinctively general relativistic stuff. For him, it was the equivalence principle is the story about how you're going to use the theory of general relativity. And then only once you have these in place do you come to what are properly empirical laws. And in this case, the gravitation as itself, the Einstein's equations of motions and so forth. And just keeping that in mind for later, this is what I think is kind of a really good way of thinking about the role that theories will play in the use of theories. And you can choose any kind of theory that you want of theories, as long as you're not doing the receive view. And the reason for that is that if you are, you're going to get into big trouble, because as we all know, that's a terrible view. This is how old do you think this guy is?
12.
Yeah, right. He's 30. That's Bill in 1973. Quite an interesting occasion. Wait. Who's that?
Looks like Hillary Putnam.
It is Hillary Putnam. Yeah. Tarsky's over here somewhere. Can't see him. Anyway, it's a terrific picture of Bill. Anyway. He's gonna explain why, so when you look into on theories, you see him very quickly take on this receive view, and it's never clear, at least to me, and maybe Chris will tell us more tomorrow. It's never clear to me what Bill's final theory of theories is, or whether he thinks it's necessary even to have one, and that might be kind of prescinding from that kind of worry. But he explains the three-tiered feature of the partial interpretations account, where you have the theoretical vocabulary on one hand and the observational vocabulary on the other, and kind of bridge laws that connect them up and so forth. And what's troubling to him about that, in print, the most troubling part about that is the way they couple this to thinking of the theory structure as somehow indicative of their theory of epistemology. And so they slave themselves in this to hypothetical deductivism. And as a result, as he says, this masks the epistemic strength of theory-mediated measurement. And a particular target in this passage is Carnap and his misuse, as Bill says, of empiricism, semantics, and ontology, where, according to Bill, what happens is, because of his commitment to the partial interpretations of counter theories, Carnap misunderstands his own argument in empiricism, semantics, and ontology, which is a purely abstract object kind of argument, according to Bill, and instead incorrectly applies it to thing talk. And about that, I'm going to demur a little bit myself. And in fact, that's not what's going on in empiricism, semantics, and ontology. Now, it's true. Oh, well, let's just read this passage here first. To recognize something as a real thing or event means to succeed in incorporating it into the system of things at a particular space-time position, so that it fits together with the other things recognized as real, according to the rules of the framework. ... To be real in the scientific sense means to be an element of the system. Hence, this concept cannot be meaningfully applied to the system itself. Now, where does this appear? It's not right at the beginning of things. At the beginning of things, it's true. What Carnap, he's lamenting his guilty feelings about using abstract ontology, talking about classes and talking about properties and so forth. And boy, I feel bad as an empiricist doing that. And if only there were a way to do that respectably, that would be great. And then he gives a completely general argument, insofar as it is an argument. It's more of a description. It's a very powerful description. Basically, the argument is what I read, that you can't think about, talk about, deal with various kinds of vocabulary unless you've embedded them in the right way in your framework of discourse. And that applies not just to the abstract. In fact, the first example is about thing talk in general. And so I think I would have to demur from Bill's view on this a little bit. But the point of all this conversation for Carnap is that it's a category mistake in a certain sense to talk about whether your theories are true or not. It's only within a particular theoretical structure that remarks like true even have any significance. Okay. Now, I'll come back maybe to this later. This, in my view, aligns Carnap with a certain kind of species of idealism. And that idealism is not the one that's subjective idealist, because, as he says, that's not a position. And it's not the realist view, because that's also not a position. But this thing that Hume does, what I'm going to call methodological idealism, that sits in about that same theoretical space as Carnap's view of things. Now, Bill's very strong, I think, on the general argument. It's not at all a criticism of that. The understanding of what's going wrong with the empiricist movement and their incorrect use of the hypothetical deductive method, I think, is quite compelling. But I don't think he's quite exactly right about the Carnap stuff. And so the real problem wasn't really the theory of theories. Instead, it was that kind of use that they would try to put it to by making the epistemology of the science itself be something that you could read off from the theory structure. Okay, so idealism. The one takeaway that's most important from, like, for example, the treatise of human nature is that you can't talk about certain kinds of things. You can't interact with things that you have no causal connection with. It's very similar, if you read it with the right eye, this story that Hume is telling is very similar to Putnam's causal theory of meaning. And unless you've got a way to connect the talk that you're engaged in with things that are part of your experience, then that talk has no significance. Okay, and that's it. So only talk about phenomena is the idea. Now, why call this idealism? I call this idealism because Hume's a British idealist, and so I've inherited the word, but I'm definitely in the market for a new word. Empiricism was taken. Positivism was taken. constructive empiricism. All the good words are taken. So at the moment, I'm stuck with idealism, but I'll take any suggestions that you all have. But why ideal? Ideal is for two reasons. Only one of them is Hume's reason, and that is that's what we have to deal with is our ideas. He also has perceptions, but if you read further in the treatise, you realize that ideas and impressions, which make up the category of perceptions, they're not categorically distinct. So we just stick with ideas. That's where you begin, and you have to work your way out. But Carnap, he wouldn't call himself an idealist, but there is this regulative ideal of finding the completed science and so forth. So anyway, as I say, if you've got a better word, I'm very into it. But why choose this thing, whatever you want to call it? If you're like me and you're like the rest of the idealists, there's just no other option. The only thing that you could be is not an idealist of the subjective sort and not a realist. You can only talk about the phenomena. And you have these limited resources that you begin with. Even objects are something that you have to posit later in your investigation. Hume is at great pains to show this, but also to show how to do it. And there's no way out of your own local perspective for Hume. You can come back to that. But this is not an against the external world. It's a quietism where you can't make sense out of certain things of that sort. Let me before we get to empiricism and idealism, let me try to situate what's going on in the project, because even folks who now think of Hume as kind of a scientific methodologist of a certain sort tend to not really know much about the structure of what's going on in the argument in the treatise. And so here's how Hume begins. He begins in a way like Kant, that we have completed science. It's in front of us for all to see. The Newtonian physics is the way of the world, and it's right. Now the question is, can I do the same thing, says Hume, for psychology? If you want to make a theory of psychology, right, a science like that, you should be a Humean. You should be a Newtonian about it, right? Because Newton's method is the one true method of science. And the problem is, over the last century, the idea about what's going on in the Newtonian method has changed from the rules for doing natural phenomena to something along the lines of postulate point particles and central forces, or postulate underlying causal agency and then work your way out from there into a full-blown theory. And the problem is there aren't any point particles and central forces in the mind. There's just no way you can appeal to something like that if that's what you want, if you want to do psychology. And so what you have to do is first show that stuff's incoherent, which he takes himself to have done, and then say, but yet the science is real. And so that tells us the rules by themselves, the causal explanations by themselves are enough for the kind of empirical sciences that we want to do. Okay. So I say this, that if you begin with your perceptions, if you begin as an empiricist without taking anything else for granted than what you're given, that should lead you to idealism. Yeah, that's all I'm going to say about that. Okay, so here's the problem, though. If you are an empiricist, especially of this stripe, where you think that empiricism leads to idealism, the big problem there is idealism has some problems. If you're an idealist, you cannot justify induction. Right? There's no evidence that if you're anyone, you can't justify induction. But anyway, this is a particular problem for Hume. But if you're an empiricist of this stripe, an idealist, you also can't say anything about the causal connection. It's not available to you as an explanatory item, and yet you need the causal explanations to do your work. And finally, there's no shared standpoint between us. I'm up here with my perceptions, my ideas, and so forth. You're over there with your perceptions, and they don't really mesh nicely. And so, what happens is that leads to a kind of relativism of its own. So this is the first thing is a justificational skepticism, but Hume says that doesn't matter, right? Because we're not in the business of justification. We're just in the business of doing science, and we know that it works. We don't have any other options, so we just move ahead. And that's great. This relativism isn't new with Hume. The relativism starts with Sextus. That's one of the main bugbears of the skeptics in the first century. And they think that there's no solution to this. The fact that my perspective is different from yours, that I taste things and I can't explain to you what they taste like, et cetera. It looks like I'm moving and it doesn't look like you're moving. All that stuff, right? That's the foundation of their skepticism. But we now know that that's not a problem if you have the right kind of a coordinative theory of things. If I have a way of not having your perspective, but being able to do an interchange with your perspective. So I can take that not as a skeptical problem, but just as a feature of our shared investigative enterprise. But then there's this third kind of skepticism. I don't know what else to call it other than structural, but it might be that your theory is self-undermining in a certain sense, that it has elements in it that are meant to explain the way the world is, but also has elements that make those elements unavailable to you somehow. I'm not going to say anything about that right now, but I'm going to claim, and this is what I'm going to get in a lot of trouble for, I'm going to claim that that's what's going on in the quantum theory, at least in this in kind of investigations I was talking about at the beginning. Okay. So where are we here? Okay, so now we're getting to the quantum stuff. It's going to be more fun. I confess, when I saw that this was a modern physics conference, I thought we were doing early modern, but then I quickly had that changed. Anyway, so Mr. Wigner's neighborhood. What's going on here? Before I say anything about Wigner, I'm just going to say some things about what's going on now in the extended Wigner friend scenarios. So I take it that everybody knows roughly the Wigner friend argument, but this is now we're gonna put that on steroids a little bit and have a whole bunch of friends with a whole bunch of labs, and they're going to have a whole bunch of interesting interactions. This is one particular version of it that's coming up. How these things work is you postulate some physical principles, you set up some labs with some agents and some super agents, and you evolve the system in just the right way so that you can then make predictions that end up essentially being Bell inequalities, or effectively that which we know are violated by actual nature. And so that tells you you have to throw away at least one of those physical principles that you've postulated. And the particular example that I'm looking at now, the most, according to Leifer and Schmidt and Ying, is the most plausible in a way. The principles require the least kind of imagination to come up with. The first is absoluteness of observed events. It's not going to be, unless you already know what you think you mean by this isn't going to help you. But if some observer carries out some measurement process and gets an outcome, then that's single and absolute. It's not you would get one, I would get one. It's relative to who's looking. That's an absolute event, some kind of outcome. And the other is local agency for observed events. This is a kind of way, what Leifer and Ying and Schmidt put it this way, this is kind of a way of trying to avoid things like superdeterminism. Okay, and how does this work? If I have a measurement that I'm going to carry out, and I have a setting that I have to set before carrying out that measurement, when I choose that setting, nothing in the future of that, nothing outside my light cone is correlated with that choice. Okay, so That's going to be useful later when we try to make some transformations in the probability assignments. But this is, just a way of saying that things that are space-like separated are really space-like separated in a certain sense. Okay, so, but these have no real empirical grounding. They're empirically motivated, but these are not observed principles. These are not things that we know to be true. These are people doing metaphysical speculation to try to preserve some notion of locality. And if you're Bruckner, you're doing it at the expense of reality, whatever you might mean by that. So here's the setup. This is really just here so I can say that I did some philosophy of physics. Anyway, you begin with this Hardy state. This is a spin system in this superposition. Oh, I'm missing a little, should be a bracket there. In a superposition of down, 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 up, and up, down. And you're going to feed this in to this machine here, or it originates from this machine here. And then the two branches of the system are going to head off. One's going to go over here to Charlie, one's going to go over there to Debbie, and they're going to make some measurements. And the way this goes is Alice here and Bob have their own measurement apparatus, and have these settings determined by x and y. And x and y in this case just take the values 0 and 1. And what they're going to do is, if the value of the setting is 1 on Alice's side of things, what she's going to do is she's going to take this state that Charlie's in, and she's going to do a unitary transformation and undo everything that Charlie's done all the way back to this point here, and then she's going to measure R. And similarly, whenever Bob has the setting 1, he's going to do the same thing and unwind it like that. And then what's going to happen, these are known empirical results. These are the probability distributions that we're going to get. If Charlie observes the spin up, then the probability that Debbie and Charlie both observe spin up when the settings are 0, the probability of that is 0. It's kind of obviously true because these are systems that are anti-correlated. The probability that Charlie observes 0 and I believe that should be Debbie. I don't know why that's a B there. It's the same thing over here with. Oh no, that's right. The probability that Charlie's going to observe 0 and Bob is going to observe negative. So he's looking in the plus-minus basis rather than in the computational basis. That's also 0 when the settings are as they're shown. And so forth for the other two measurements. These are empirically confirmable and have been empirically confirmed. Okay, so none of this implies anything at all about realism or locality or anything at all at the moment, just because we don't have any of the conditionals the same. So that you can't infer really anything from those probability distributions when you have different conditionals. But if you do things right, you can turn all of those conditionals into the same settings. And here's how that works. Because we have this principle, local agency, it shouldn't matter whether I come here and change the settings on runs where I'm not actually doing the intervention. Okay, so whenever I like, I can change these ones in the appropriate way. And according to this, now we do have a problem. Well, at least we have a contradiction, because you can chain together the probability assignments up here and get it to be that the probability of A minus B minus is not 0, but the 3 up there imply that it is 0. Okay. So what are we supposed to conclude from this? We have to conclude that at least one of these principles that we use is incorrect, whether it's the absoluteness of observed events or the locality condition. Now, I don't really have anything to say about this particular experiment, but instead I'm concerned about the whole culture of the super user tool that folks are using. It just, I don't know if it's only an intuitive worry, but it should be that when you make a measurement, it should be stable. This is for many people, the fundamental principle of empirical science. But if you're using these no collapse theories, a many worlds theory or a single world theory that has super users in it, or even the Bohm theory, if I understand Zerovici's argument properly, there aren't any stable measurement outcomes because it's always possible to undo any measurement outcome with the right application of a unitary. And so this strikes me as a corrosive skepticism. It's a skepticism about the possibility of measurement in quantum mechanics. And that's to be eschewed. Okay, so let's quickly talk about the Ur friend here. Now, Wigner himself seems to be an idealist, if I understand him right, and I don't quote him here about that. But here's why you might think that he's an idealist. It's perhaps important to point out, and this is in the Philosophy of Mind paper, it's perhaps important to point out at this juncture that the question concerning the existence of almost anything, even the whole external world, is not a very relevant question. All of us recognize at once how meaningless the query concerning the existence of the electric field and vacuum would be. All that is relevant is that the concept of the electric field is useful for communicating our ideas and for our own thinking. The statement that it exists means only that it can be measured, hence uniquely defined, and that its knowledge is useful for understanding past phenomena and in helping to foresee future events. It can be made part of the Weltbild. This observation may well be kept in mind during the ensuing discussion of the quantum mechanical description of the external world. And so Weltbild is the system of phenomena, if you like. Anyway, so the standard Wigner friend, just to say it out loud, is Wigner is thinking about observing a flash and figuring out from observing or not observing a flash what the wave function is subsequent to that. And instead he sends his friend to go check. And what standard quantum mechanics says is as soon as he sends his friend out and his friend starts to interact with the system, then the friend goes into superposition, right? Then standard. And when Wigner receives a report, only then does the friend collapse into a state of having seen or not seen a flash. On the other hand, that seems like an implausible way of treating your friends. If your friend comes to you and you've made this measurement and they've told you what the outcome is, for you to then ask again, yeah, but what were you seeing before I asked you? And the only option here is to say what I already said. Then, and I don't quote it here, but then Wigner says, that sounds like a species of solipsism. And nobody could possibly take that particularly seriously, and nobody could want to be found in the position of being such a person. But I guess my question at this juncture is why not? First, that's obviously not solipsism, right? I think we can all agree on that. Solipsism is I'm the only mind. This is, there's something about my mind that in certain ways of understanding the world or in certain moments is different from how I'm understanding your mind. But that's not at all solipsistic. And so so Wigner leaves us with this challenge, like who would want to adopt this view? And so I've said, hold my beer, I'm going to adopt it. And so that's why I think we should move on to what I'm calling a single user quantum theory. Now, I don't think this is Rovelli's view, but I don't think it's not. I think it will depend on who you ask, and it'll be true whoever says what the answer is. Anyway, but I think there's an asymmetry that's sort of built into this whole way of allowing super users come in and turn people backwards that's not reflected, if you like, in the phenomena, okay? And when we see such asymmetries, it seems like the right thing to do is to erase them by proposing a relativistic theory, right? This is what we're all familiar with from the electrodynamics of moving bodies. It's the same puzzle situation in a certain sense. But what's relative? And this is where I think I might disagree with Rovelli. Maybe I don't. I say that what's relative is the quantum state, but it's not relational. The quantum state is absolute. So here's a distinction that, as far as this is anecdotal, but I think there's a distinction that every single philosopher thinks is a difference between relational and relative, and not one single physicist thinks there's a distinction between relational and relative. I'm happy to be corrected on this later, but I haven't seen anybody who would admit to it. Anyway, but what's going on here? I'm proposing a kind of a tiered structure, right? You have exactly the mathematics of Hilbert space, but now the mechanical part is not the quantum bits are not properly empirical. They're structuring, they're framework, background stuff. And in a way, I wanted to put Michael's slide up here because I'm not sure that this was an option on that slide, because you said, I think, that even the background theories they're structuring the properties. And I don't know that that's right. I think it's more telling us how to use the theory, the Schrodinger dynamics and the collapse postulate. So here's the idea. The quantum state is absolute. It's not relational, but it is relative. And so in that sense, not absolute. And there's just the one user, and that's me. And everybody else is in a Schrodinger evolution. But when I get sufficient information that can allow me to distinguish between two elements in a superposition, say, then they collapse into that state, the state that I've observed. Is this somehow privileging me? Well, it's not privileging me any more than saying that I'm right now at rest in space, and anybody who's moving with respect to me is not at rest in space, right? It privileges me, surely, but anybody else can say the same thing. So it's not there's no asymmetry here. It's just only one at a time can you use quantum mechanics. And if we happen to be close enough to have a conversation about it, then we can give ourselves the idea that we're both doing it at once, right? And so that's it. That's the view.
Okay, thank you for that. I just wanted to get clearer about what this single user quantum mechanics is, because as you probably know, the cubists say that quantum mechanics is a single user theory.
Yes, right.
And what they mean by that is I use quantum mechanics to predict, my own future experiences, but not what you will see. Is that what you mean?
No, I think I'm going to predict what you're going to see as well.
Okay, that's good.
So here's the thing about this collapse view, and here's, if you like, another way of putting the central mystery of quantum theory is, how is it that when I have you in a superposition state and I make a measurement and collapse you into some definite state, you also, at that moment, must be collapsing me into that definite state, because now we're doing the exact same thing together. And so you'll get the same result that I will. I'm going to think of you as in superposition until then, but presumably you're thinking of me in superposition until then as well, when you're using the theory.
Okay. It sounds kind of like Heisenberg Copenhagen with a movable cut. I mean, one of the things that's weird about the whole extended Wigner friend analysis, going back to Fracture and Renner, is they're essentially using like a Copenhagen style movable cut, but
But a cut that,
but you're using two different choices of
Right.
cuts in the same analysis, and Heisenberg never said you could do that, right?
right. So that is a serious problem with the Frauschige-Renner, with all of this super user stuff. But I don't think that's going on here. I'm the only one who's making a cut right now. Okay. And it's not that I'm thinking of you as unreal or anything like that. I'm just thinking of you like a normal quantum system in a superposition state of various other kinds of things. And you're not getting very far in superposition because I'm like really close to you, really clearly taking data from you and so forth and getting information from you right now. But if we were space-like separated, right, then I would examine my qubit, and then I would collapse the wave function. And that's going to happen at the speed of light. It's not going to be an instantaneous collapse. But when I finally come together to compare results with you, you're doing the exact same thing, Yeah, so there's only the one cut.
Okay, good. All right. I have other questions, but there's others in the queue.
Carlo, do you want to come to the mic? And I'll bring this one to you. And then Simon, you're next.
Thank you, and I love this. Of course, your arrival point. You did this beautiful long construction. At the end, you said how you think about quantum mechanics is one slide. In just your closure, very fast.
Yes.
I fully sympathize with that. That was my starting intuition, right? So it's quantum mechanics is how I describe the world, and Chris used.
It's not how I describe the world, it's how the world is.
How the world is, yes, and so does Chris, and I'm a quantum system for him, and this is how it makes work. But so I just wanted to express sympathy. But the question is about you said no philosopher and no physicist. Can you explain a stupid physicist what is the distinction between relative and relational?
Well, consider
What do you mean exactly by precisely that?
Consider the following conversation between Fred and Ike about the structure of space. Fred thinks that space is nothing more than a codification of various kinds of relations between all the bodies that there are. And Ike thinks that there's a pre-given absolute structure in which all the events of those bodies unfold themselves. Ike, in this sense, would be an absolutist about space-time structure, and Fred would be a relativist, or a relationalist about space-time structure. But suppose later they're having a conversation, with, I don't know, some relativist, right, who wants to explain to them that the structure of events, right, when you transform from one stationary frame to another stationary frame, right, that doesn't work the way that you thought it did. That you have to have a relative view of that, right? There's no such thing as absolutely at rest. There's no such thing as absolutely in motion. And so Al has this conversation with the two of them, and they both walk away from this conversation. They're like, yeah, wow, that's right. So now I'm a relativist about spatial relations. I'm a relativist about temporal relations. But if I'm Fred, I'm still a relationalist, not an absolutist about structure.
The different remains. Yes.
They're distinct kinds of views, and yes, they come from the same word, and so it makes one think that they're the same idea. But my look over at the history of physics doesn't make it seem like they're doing the same things, relationalism and relativism.
Yeah, I got it. Thank you. Yeah.
Yes, well, thank you. But I really, I just wanted to know whether indeed your single-use quantum theory is Carlo's view.
I want to know that too.
Yes, so please, Carlo, tell us.
Yeah, I want to know that too.
Yeah, we can. Yeah.
I'm tempted to say yes, but I would hesitate before.
Well, sometimes when I read Rovelli, I got the idea that even measurement outcomes aren't absolute, and I find that a little troubling. But maybe maybe if I'm representing
No, but what I mean by measure outward and not absolute is the following. I'm here, I make a measurement outcome. I see that this is red, period is red. What I mean, this not being absolute means I still think that it's possible that there is some user somewhere else that could find interference effects between what he would call this branch and some other branch. He could use that language if he was Simon. That doesn't deny the existence of interference effect.
It doesn't deny the existence,
which we think you would agree.
I would agree, but I would also expect that when that other user comes into your, if you like, quantum frame, and you have a conversation, you're both going to agree that.
Then we agree on everything. Yes, absolutely.
Okay.
Yes, absolutely.
Then Simon, probably it is. Probably it's just relational quantum mechanics.
Yes,
yeah.
exactly.
And so I'm very, if that's the view, then I'm happy to have, said some things about the history of philosophy that, connect it up.
Thanks. First of all, I endorse what Wayne said. Second of all, I was just wondering if you could elaborate a little bit on what you mentioned and kind of in passing, about my slide or about the slide. Maybe I could.
So I thought when I saw that slide about the interpretations of quantum mechanics and so forth, there was the bit about the Bohr and Heisenberg and so forth, and that quantum theory is now I can't remember exactly the content of it. The slide I'm talking about?
Yeah.
So I wasn't sure at the time, and so I wanted to ask you whether thinking about the quantum theory, Schrodinger equation, and collapse and so forth as a structuring position rather than a position that's directly about the features of, say, electrodynamics or bodies in motion and so forth would count as one of those instances. This was just, it was very hard to read this. All it said was background, and I wasn't sure what you meant by background.
I thought you meant something else. I thought you were asking something else. But I mean, what I meant there is just structuring in the sense of it places constraints on any specific dynamical story you want to tell about a system. But
Okay.
it is directly. It does directly place constraints.
Sure, but a constraint, not a.
A
So
constraint.
sometimes
Yeah.
So here's how you sometimes end up in conversation with Tim Maudlin, right? The question, and Shelley Goldstein as well. Okay, I won't comment. But I sometimes think it's not a good idea. So maybe we could talk more about that at dinner. And Shelley the same way, right? The thing that miffed them the most about Jeff's version of quantum mechanics is that he said that quantum mechanics is about information, and it's not. It's about electrons and whatnot, and so it's directly in the physics. It's not about the physics. And you could have an information theoretic view that's kind of compatible with this, where you ask what's missing when I try to translate between the quantum users, right? There are these constraints on what possible information can flow, from various quantum systems to others.
Wayne, I think you should get over there.
Okay, thanks. I mean, I do get in conversations with Tim Maudlin, so I'm not sure it's actually a mistake. But sometimes I wonder, are we recording this?
Tim could well be watching. You can look at the list.
Anyways, I just want to express a reservation about what you were calling corrosive skepticism.
Okay.
Because suppose someone tells me there are super observers that could, in principle, undo any measurement. That means that any measurement result can be erased. It doesn't mean that that they all will be erased.
Sure.
And we're just familiar with the fact that in ordinary life, any measurement record could be erased, and a lot of them have been. A lot of experimental results that have been performed got destroyed and they never published and things like that. So I don't think that saying any measurement record could be erased a massive corrosive skepticism, but also they actually need something just a little weaker. What they need is some things that we would count as measurement results can be erased. And when it comes to actual experiments, you learn, you talk about Charlie and Debbie when you're doing the things, but then you do experiments, and it turns out that Charlie and Debbie can be photons, and pretty much anything can be an observer, right? And there's a reason why Charlie and Debbie are in hermetically sealed labs, because if I doing if you have a super observer who can undo what happens in this hermetically sealed lab, it doesn't follow that they could undo every single measurement result, because there might be limits to what they do.
Sure.
What they can do. So, for example, I write something down on a piece of paper. Photons hit it. Some of them go off into interstellar space, and maybe the super observer can't track down all those photons and erase and reverse them.
So that sounds like a practical problem. And so
What you're saying is the argument does not require the possibility of erasing every possible measurement result. Only that it requires the possibility of some.
Well, I'm pretty sure it requires the possibility of erasing any.
No, it doesn't. It only some.
Not all, obviously, but
no. What the argument requires is there are some things that we would count as measurement results that can be erased.
Okay. Simon also has a question.
Yeah.
I don't know if you want.
well, I just in any case that there's still this skeptical worry. It's not so if you're skeptical about, say, the theory of knowledge, and it's some built into your theory of knowledge that you, on the one hand, need any statement to be justified in order to accept it as an item of knowledge, and there's a certain class of statements about which you're committed to those counting as knowledge statements that fall under the class of things that cannot be justified. That's a corrosive skepticism, even if it doesn't address every possible element of your theory of knowledge.
And I've really got more of a finger on this than a hand, but all of this is dependent on these super observers and super technology and so forth. And one can launch the same sort of argument just within classical thermodynamics and statistical mechanics. So I'm not sure why this is a corrosive skepticism. Certainly specific to quantum theory, one could say the same as I say about.
Oh yeah, I think that's a good point. And I was wondering about this exact question. And I'm going to talk about David Albert for a second. One thing that at least is motivating of the Time and Chance book is that the statistical mechanics is corrosively skeptical, and if you don't want it to be overwhelmingly likely that we just now tunneled out of the vacuum, then you need something to stop that. And maybe you don't like the solution of the past hypothesis, but that's what it's doing. That's a law-like emendation of statistical mechanics that prevents that kind of corrosive skepticism. So I totally agree with you that on my account, that would be corrosive skepticism, but I also don't like that.
Yeah, but that's a rather different point. I mean, there the issue is, why do we not infer back in the past into a high entropy state in the past, and we're just in a low entropy dip and so forth? That's a different sort of problem from the Maxwell-Demon sort of analysis, which would correspond to your super observer using super technology. A Maxwell-Demon could reverse all of my storage in memory and so forth by careful manipulations and so on and so forth. So that's dependent on the super technology.
Yeah.
It's different from that.
That is, but this reminds me, I didn't quite fully answer Wayne. I don't think that those are the same. It's not that I erased your memory. It's that I erased the fact that you did a measurement. Right.
Well, that's a very tendentious, it's a very controversial way of framing it.
I don't think that's true. I think that on these accounts, something happens and you get a measurement result, And then the super observer does this unitary that basically, in order for it to work, it has to destroy any record of the result. But it's still the fact that experiment did happen, and if you accept the absolute absolute remeasurement results things, there was a result. Right. And in fact, the argument requires the argument requires there to have been a matter of fact about what that result was before the super observer did their thing.
Okay, so it's one thing for the argument to require a thing. It's quite another for that to be an appropriate thing. And it's not at all clear to me that there's any sense that one can make out in which there really was a measurement. That's just a dogmatic stipulation. As far as I can tell, the system is in superposition the whole time, and therefore either there's a collapse, in which case it comes out of superposition, or all the measurement outcomes were realized distributed according to the Born rule. It's not there's
there was this quantum state was the superposition and there was a definite result.
What does that even mean? That means there are all these definite results.
That's true in the Bohm theory.
Well, the Bohm theory is not really in a superposition because we have the magic of particles.
The quantum state, what I said is the quantum state is in a superposition and there's a definite result. That's what the Bohm theory says.
Because we have the extra
exactly.
lighting up of particles.
That's one of the options, That's one of the ways to make the absolute. So ways to make that condition that you had, absoluteness of outcomes. One is unitary evolution of the quantum state, but hidden variables. And the other one is a collapse theory. Because if you've got unitary evolution and no hidden variables, then you don't have that absoluteness condition true.
Carlo also. Did you want to say something?
I do. So I agreed in a certain sense about the Bohm theory. This is something I did want to ask you about in particular, because I was reading that Larizzi and Hubert paper, and the sense I got from that is, at least epistemically, you can never be in a position to know that what you've done now has got a measurement outcome. Because because there's always the possibility that there's going to be some unitary later that's going to undo it.
Sorry. On the Bohm theory, there is a measurement outcome, and you can't know for certain that there's going to be any permanent records of that outcome because you don't know that someone's going to erase it. But you know what? That's always true. Like even in ordinary classical mechanics, you're never guaranteed there's going to be a permanent record of your measurement outcomes.
Yeah, no, certainly not. We'll have to talk more about the Bohm theory, but as far as the no collapse theories that have definite results but nothing enforcing those results, that seems to me to be a problem.
This is naive again, and I want to bring back the discussion away from the technicism and to the general philosophical thing that you started from. The fact that I agree so much with you in the way you put all the last part of the story, does it mean I'm an idealist? Like
I don't think it could possibly mean. It certainly couldn't mean. It certainly couldn't mean that. I think probably so.
So I guess the question is how much the second part requires the first part. Is that?
So I wouldn't say that the second part requires the first part. It was, from my perspective, it's more does the first part enable the second part?
Yeah.
But
idealism here, what you meant by you said you just chose a word.
No, I didn't choose a word. I inherited a word.
But you said you hesitated about.
Yeah, I mean, I would like to get a different one, but that's the one I didn't choose it. I inherited it.
But is it the sense of Hume, not in the sense of the German idealism, as not even in the sense of the.
Well, it's not a million miles away from the critical idealism.
I see. But if one add the words mind to that, is needed or not? Or theory is sufficient?
I think theory is sufficient.
Okay, but that's big jump. So there's no
Well, so
mind.
so
It's not the world.
it's not a it's not a so
not
that's
spirit, mind.
it's not a subjective idealism.
Okay.
And so that's one
That's what I wanted to.
that's one partial answer to the question, why did idealism get such a bad rap in the 20th century? It's because in certain circles
what I
it was
want to
identified with subjective idealism rather than, for example, the critical idealism or a Humean idealism.
Oh, you mean with respect to a transcendental point of view or something like that, in the Kantian sense, not in what came after. So there's no mind here. That's the point.
There's no need for mind in this
Okay.
version of idealism now.
Okay, thank you. That's clarifies.
I think Simon.
Well, I just wanted to make just one further comment relating to your suggestion, James, that the outcome never happened. That with the erasure, as it were, the outcome never happened at all. But it seems there's a fairly obvious sense in which it must have happened, because whoever is performing the super technology, the super observer, had to get involved with extraordinary manipulations precisely to undo that outcome. So that super technology person absolutely knew that outcome happened and then had to undo it. So what is your response to that? It seems such an obvious flaw with
like if I were the super user, here's how I would think about that. I would think that the system is in superposition, and one element of that superposition got extraordinarily tangled up with a bunch of other stuff, and I had to undo that tangling up with that other stuff to bring it back into a superposition state, or to reveal the fact that it was still a superposition state the whole time. And I would never think of that as being a definite outcome.
Well, okay, but then this isn't so much that the event in the past did not occur. It did occur, but the super observer would not describe it in terms of a measurement outcome having taken place. It was just a certain unitary dynamics that took place.
Certainly.
Right, but the way you were framing it was that unitary dynamics did not take place either, because the records of it have been erased and so forth.
No, the way I'm putting it is that person didn't get an outcome because that person isn't that branch.
Okay, but whatever that person was doing, whatever was going on at that time, did in fact take place, and all records of it was systematically erased by the super observer.
Sure, as were presumably the other branches that did take place.
Right. So
so the sense in which we get to say did take place, but also still in superposition, that's what eludes me.
Right. But I think what I'm getting at is it's not so much that this leads to, as it was, there was no past. It's just that what happened in the past should not be described in terms of somebody getting an outcome on performing an experiment.
Certainly
Something
not.
else happened in the past.
Yeah.
Right.
But that's exactly what I meant.
Slide with the local friendliness conditions. Yeah, if I want to say something about those. Okay, yeah, so basically any interpretation, I don't like the word, but any approach to understanding quantum mechanics already has a way of understanding what goes on in these Wigner friend experiments, and so any so-called interpretation is going to violate at least one of a set of conditions that leads to a contradiction, because it's just consistent. And so if you think, and you just go through various approaches, Everettianism, you're not going to get a contradiction from that, but that's because it denies the absoluteness of observed events. There isn't a single outcome that occurs. You get branching, and you see one outcome on one branch, and you see another one. Another branch in the real world, this branching tends to be permanent, but the super observer can undo it. So what kinds of approaches would have this absolute observed events? Well, if they're approaches in which the quantum state evolves unitarily, then they're hidden variables theory. So, something like the Bohm theory would satisfy that absolute of observed events, but something like the Everettian theory would violate it.
And then would have to violate, in that case, the free choice.
No. Yeah, yeah, It
Which
violates
which
local
which Bohm
yeah. So
which Bohm certainly does violate.
on the Bohm, on the Bohm theory, you choose, out choice of experiment on one wing affects the result
Right.
on the other.
Yeah. It has to, because
Yep.
it has to violate one.
It has to, yeah. Yeah, so like there's like I think it was, I forget whose paper it was, that there was a paper with the title, was it the Bruckner et al. Paper? The title was quantum theory, or maybe it was Fraser and Renner paper. Quantum theory cannot consistently describe
That's Frauschiger-Renner.
itself. And then in the paper, there's a list of ways quantum theory can consistently describe itself, because it's not like these various approaches to interpreting quantum mechanics have to make adjustments every time someone comes up with a new thought experiment. The Everett approach already has built into it what they're going to say about this. The Bohm theory has already built into it what they're going to say about this. The collapse theories do. And basically the Lazar Ricci-Huber paper is just going through, here's a consistent one world story that the Bohmian would tell about this sort of thing.
Sure.
Yeah.
Yeah, I mean, that's all right. The only comment I would make is that the way Frauschiger and Renner did it is they thought that these were principles that you really ought to subscribe to if you're doing quantum theory. And the way a lot of the quantum approaches avoid them is just by throwing away essential features of things.
Well, yeah, but and this says something about the mismatch between people who've been working in philosophy of quantum mechanics for years and physicists who are discovering it and coming out from the outside. So we're all familiar, like those of us who've been doing this for a long time, are all familiar with, in light of quantum mechanics, something that you would have otherwise taken for granted can't be true. I mean, that's just something that everyone who's been thinking about foundations of quantum mechanics for a while knows, and we're familiar with the fact that any approach to the measurement problem will give up something that we would have otherwise just taken for granted. So, and there's a real sense in which this literature is in fact reinventing the wheel. And I mean that seriously, because the structure of the Frauschiger and Renner thought experiment is identical to the structure of my modal interpretations and relativity paper from 2002 or whatever. It's exactly the same thought experiment, except I didn't talk about observers. I just said, okay, suppose there's a theory in which some observable is always definite. And that could be, whatever it is in the brain that the observer's experiences supervene on. So there really is a in all this extended Wigner's friend literature, there's an element of physicists who are just now starting to get to grip with these things, sort of recapitulating discussions that have been going on for years.
I think that was just getting sort of a great discussion.
Yeah,